Hey, good afternoon, guys. So this is the last talk of the day, right? So hope you guys are all here to learn stuff. So I'm going to talk about the internet. Why am I talking about the internet? I have some qualifications. I've been doing a few things with the internet for a few decades. So what you're going to learn about today is some basics. The reason I'm presenting this talk at this BSides and at other conferences is that I think a lot of folks, particularly in InfoSec, just really don't know how the internet works from a practical perspective, and you don't have the context and history. You are not going to become an expert, but you're going to get a sense of how things work and how things have continued to scale on the internet historically. And we're going to answer the question from the talk about why is the internet still working. And if you guys have any questions at the end, that's great. So here's a basic thing. What is the internet? Everybody talks about the internet. So it's a global telecommunications system that we think is pretty essential. Why is it called the internet? Well, you almost never hear this term anymore, but back in the old days, people used to talk about internets, lowercase I. Collections of networks that were connected together. The internet was a capital I, and I still firmly insist that the internet should always be a capital I. Things like the AP style guide disagree. They are wrong. Be corrected, because the internet is the global collection of all of the internets in the world as a whole. They all just happen to use the same protocol. That protocol, magically enough, is called Internet Protocol, IP. That's how they interoperate. Of course, this is the real answer. We know that the internet is a series of tubes, and they're filled with cats. So how do you get connected to the internet? I mean, I hear it's the thing that all the kids are doing these days. So you would generally buy access. I can remember a day in which you couldn't actually pay to get on the internet. You had to be like a student or a researcher. So you buy access from an internet provider. Might be your cable company, might be a cellular provider, satellite, fiber to the home, whatever. But you're buying an access from this internet provider. So where does the internet provider buy their access to the internet? Well, that's an interesting question. So in order to answer that question, we have to go back in time and give you a little bit of a, you all right? All right, give you a little history lesson. So you probably all remember that the internet started off as a DoD research project and started off in '69. The original protocol on the internet was called NCP, used up to 1990. So the ARPANET was the forebear of the internet. And what you're seeing here is basically a baby picture of the internet. December 1969, 4 nodes. A whopping 2.4 kilobits per second, later upgraded to 50 kilobits per second. Really fast. The internet grew, or I should say the ARPANET grew. Here it is in 1971. You've got some West Coast and some East Coast and a little bit in the middle. And these are all the usual suspects in terms of research institutions and government agencies. The ARPANET grew pretty quickly, as you can see here in the terms of the total number of nodes, from 71 40 nodes to 87, 28,000 nodes, and then 2 years later, 80,000 nodes at the beginning of '89, 160,000 nodes by the end of that year, doubled 1 year. This sort of network effect continues to this day. Here's a little bit of additional adolescent pictures, I guess, the ARPANET, 1980. I can remember when UUNet started. I wasn't there, but I remember. I remember when the NSFnet got upgraded to T1s, 1.4, or 1.544 megabytes. So these are all ancient history days. So TCPIP, it is the protocol used on the internet today. Heard about it. Took 10 years of development. And I want you to think about that protocol that everybody uses that you're still doing the vast amount of your work on the internet with was developed in the 70s and deployed in the early 80s. Just think about that. Standards never die. So right now there's actually two different versions of TCPIP. Some of you have probably heard of IPv6 versus IPv4. So you've heard this term, internet addresses. You should know what they are. It's this 32-bit dotted quad address. Every device should have a unique address. There is network address translation. We'll get to that later. IPv6 changes that. It's 128 bits. Very different. So there really are two separate internets. And people don't think about it that way, but it really is true. They are almost always running on the same physical infrastructure, but logically and from a protocol level, there is the internet version 4, IPv4, and IPv6. There isn't really a whole lot wrong with IPv4. It works. It's worked for decades. The biggest problem is that we've just run out of IP space. We've run out of addresses because there really isn't enough addresses for everybody to get one. Well, it's not true. There's more and more IPv6 deployment, but there are IPv4. I'll show you. So how do you get an IPv4 address? Well, you at home, certainly you get it from your internet provider. If you're an institution or a business, you want to get your own IP addresses. I highly recommend that every institution and enterprise business that wants to connect to the internet, you should own your own IP addresses, that you should not be getting them from your internet provider. They should be yours. There are still ways to do this. That gets into having different blocks of IPs. IP subnets are just ranges of addresses. They can be anywhere from 2 addresses up to many thousands. Again, if you're at home, you get like a single IP address. It's typically a dynamic address. It changes periodically. But if you're a business, you probably have a static IP, maybe have a whole subnet that you own. So again, IPv4, 1983, 4.2 billion total IPs. That's really the biggest problem. We have too many people, too many devices on the internet. And today, with the Internet of Things and everybody wanting to connect their toaster and their refrigerator, and I'm not even joking, to the internet, they all need IPs. Now, fortunately, we came up with some technologies, the internet community, called network address translation and port address translation. And this has really extended the life of the v4 internet immensely. And this is what you do at home. If you have and almost everybody these days, you have a little network of some sort at your house because you've got your very important Netflix streaming device connected to your television. You've got some iPads. If you've got teenagers in the house, you've got all kinds of devices. You've got your refrigerator. You've got all these things. And you have an internal network in your house. And you have a single IP address that you get from your internet provider. Well, that's called network address translation and PAT, port address translation. All of your requests and all of your connections out to the internet from inside your house go from a single IP on your router in your house. People typically call it a router. It's really a firewall / router for your home. So IPv4 has a whole bunch of special reserved subnets that you should be aware of. If you are doing pen testing work or you're doing network analysis work, you should know what these are. There are many Wikipedia articles about them. There's special address ranges that have special meaning that are reserved for internal use or documentation. IPv6, it's big, huge. It's just ludicrously large, 10 to the 38th in terms of IPs. Initial development in '98. Much larger hexadecimal addresses. And it's been getting deployed, but not as quickly as we'd like. Talk about fees. Slides are out of order. Oh. So you can buy IP addresses if you're a business, enterprise, institution. In the old days, you could just ask. You could just fill out a piece of paperwork, literally, and say, I want some IPs. And Aaron would say, great, here you go. And you didn't even have to pay for them. Like, it was just, they just gave them to you. Easy. These days, there is an annual fee that increases based on how much address space you are holding. So if you're a very small company or a small internet provider and you have a few thousand IP addresses, you'll pay Aaron a couple $1,000s a year, roughly, for the privilege of maintaining a database entry for those IPs. If you're somebody very large and you have a lot of IP space, like you're a Microsoft with Azure, your Oracle, or your AWS, you're writing some pretty big checks to Aaron every year because you have millions of IP addresses to handle all of your. So you've probably heard, it's been in the news for 3 or 4 years now, that IPv4 is what they call exhausted, meaning there isn't any more address space. The internet's closed, everybody go home, right? Well, turns out that's not actually true. But it's now very difficult to get address space from the different regional internet registries. What a lot of people don't realize that depending on where you are on the planet and which registry you've signed or not signed legal agreements with, those IP addresses are actually property that you can buy and sell and trade. Sometimes, if you've signed certain agreements, they're not. They're more like software. You have a license to use the address, but you cannot sell it or trade it. Call the lawyer. So you can actually still buy. You can still get IPv4 addresses. You have to purchase them unless you have some very specific edge cases. Cost money. ARIN, the American Registry of Internet Numbers, which covers North America, they don't have any more IPv4 address spaces available for businesses or personal or enterprise. Well, they have very, very few. You're probably not going to get any. However, you can fill out the paperwork and they can approve you and say, you can get addresses. We don't have any, but if we had some, we'd give them to you. And that means you're approved for the marketplace. There actually is a real, not gray market, not black market, a legit marketplace with brokers, and you can buy and sell addresses. This is how very, very large companies like Oracle, when Oracle started up their cloud hosting service, they needed a lot of IPs. They couldn't just get them. Aaron didn't have any, so they had to go to market and work with brokers and actually obtain addresses and spend big money. Well, because version 6 is a separate network. If all of your servers only have IPv6 addresses, you can't access them from IPv4 land. But the reverse is not true. If you have an IPv6 address, there are many technologies like NAT64 and others. There's a whole bunch of technologies that will let you access the IPv4 internet from v6 land. So in the market today, if you want to buy IPs, about $5,000 for a /24, that's 255 IP addresses. That's what basically is the minimum that you can route on the internet generally. There's other ways to get IPs that people don't know about. You can actually join RIPE, which is the European Internet Registry, and you become a local internet registrar. And for about 34.50 euros, you can get a /22 by filling out a bunch of paperwork and giving money to RIPE. So that's about 1,024 IP addresses. So that's much more cost effective than buying a /24 in the market. If you need more than that, sorry, you're going to have to write some checks. If you want like a /21, that's going to be like 50 grand. So IPv6. So what's driving IPv6, and everybody should be using IPv6, but the smartphone that you most likely have in your pocket is probably only using IPv6 when you're on your carrier's network. So if you have T-Mobile, Verizon, even AT&T, T-Mobile and Verizon, over 80% of all of their network traffic is IPv6 native. One of the big reasons that this, and it's really the cellular carriers that are driving IPv6 adoption. Why is that? Well, everybody gets a new phone every couple of years. You're updating the software fairly frequently, the different, well, Android less, but that's another topic. But because the endpoints are being updated regularly, and they're not controlled by an old archaic IT department, IPv6 has gotten deployed pretty expansively in the mobile world. This is Google's view of IPv6. This is from April of this year. Globally, about 14% of all traffic to all Google properties was IPv6. As of today, it's up to 17.25%. So 3% growth just this year. It's still under 20%, but it's growing, particularly in developing nation areas. So China has so many people, and there's so many people getting online for the first time in China, that the vast, vast majority of internet access in China is IPv6 only. You will not get an IPv4 address. You can talk to the IPv4 internet through these gateway services. So this is some data on V6 traffic sources around the world. Again, Verizon Wireless, T-Mobile, and other, if you look through this whole list, it's mostly wireless carriers around the world that are driving that V6 traffic. So I want to give you some vocabulary because also notice people don't understand the right vocabulary, using the wrong words. So routers and routing. So a router is just a specialized device that connects one subnet to another. And it routes traffic. That's what it means, is it's taking packets from one IPv subnet, IPv4, IPv6, doesn't matter, and routes the packets to another subnet. They can be small devices in your house that you maybe spent $100 on. They can also be very large commercial devices from companies like Cisco and Juniper. And more frequently, they're just software that runs in virtualization on commodity hardware. A firewall is not a router. It can do some routing functions. Basically, a firewall is a device that's controlling access. That's really the difference, is that the firewall is you're able to set some sort of administrative policy. You're able to say, I want to allow you to connect to this and not allow you to connect to that. And there's all sorts of fancy firewalls in the market, like Palo Alto and others, where you can block specific services. You can say, I do not want my employees to ever use Facebook at work. Or I only want the marketing department to be able to use Facebook, and only these specific pages, so forth and so on. Your firewall is usually doing this network address translation and port address translation in v4 networks. There's all sorts of vendors out there. Again, firewalling has become something that can be done in software, on commodity hardware, more and more. And you can spend as much money as you want on these devices. IP transit. So this is the thing that you are buying. If you're a business or you're at home, what you're actually buying from your internet service provider is a thing called IP transit, which means they are connecting you to the internet as a whole. It's what you think of as being internet access or dedicated internet access. It means that you pay a fee, and the internet provider says, I will connect you to the internet. And the way the internet has always traditionally worked, and hopefully will continue to work as long as we maintain some level of net neutrality, is that you just pay your internet provider. You're not having to pay a separate fee for every other network that you want to access. Yes, if you're subscribed to Netflix or some other service, you're going to pay them a subscription fee. But at this point, at least around here, you don't have to pay additional fees. It's not like long-distance calls. Of course, most of you probably don't even remember paying long-distance calls. is also as part of buying IP transit, you usually get your IP addresses from your internet provider. So the internet providers, they all have this thing called autonomous system numbers. And every internet provider has an ASN, and it basically identifies that organization, whether it's an ISP, a business, an enterprise, a hospital, whatever it is. It's essentially your identifier on the internet under a common administrative control. And this is how all the network operators talk to each other. Everybody has to have an ASN to route between each other's networks. It's not hard to get an ASN. There's plenty of them available. Some paperwork, $550 one-time fee, $250 a year. You get your own ASN. If you do not have an ASN of your own, you're using your ISPs. And if you do not have an ASN of your own, you're not really running an enterprise level or service provider level internet connection. You're using somebody else's resource. So here's some examples of ASN numbers for organizations you are familiar with: Facebook, Amazon, Microsoft, Apple, etc. Some organizations have multiple ASNs. They might choose to have their network divided up, say in Europe, Asia, North America, and they use different ASNs to differentiate it. Why do we have ASNs? Well, again, ASNs are to identify each network individually. They use this protocol that you probably heard of. It was in the news this week a fair bit. Border Gateway Protocol, or BGP. And it's a routing protocol, which is how the different network operators exchange routes with each other, talk to each other, and tell each other about where the subnets are and how to get traffic back and forth. If you are not running BGP and you do not have an ASN, you are not a network operator. If you're not running BGP, you're generally a customer or an end user. For example, here at Delaware Technical Community College, they have their own IP block. They have a /16. It's a lot of IPs. They don't run BGP themselves. They're actually buying all of their internet access from an ISP. The ISP is routing the traffic on their behalf. They're not actually operating their own internet connection. So why would you want to run BGP? Well, it's the protocol that allows you to have redundancy and resiliency and reliability on the internet. Any large enterprise, any institution, anybody who really wants to have a real internet connection, you have to run BGP. It allows you to have multiple connections and be able to balance traffic across in multiple directions, either load balancing or redundancy. It also enables you to do peering, which we'll talk about in a minute, and the big reason to run BGP, particularly if you're any kind of a size business, you have your own IP addresses and you run BGP, you cannot be held hostage by your vendors anymore. By having your own address space, which doesn't really cost that much money, and running BGP routing, you are now free to buy and sell connections to the internet without having to renumber, without having to go through a super complicated process. You can now just go out and put out RFPs or negotiate with vendors, and you can do short-term contracts instead of long-term contracts. And it's really what every, I would say, medium-sized business on up should be doing. BGP routing table, it's grown very large over the years. It's actually over 700,000 entries now. Like most graphs related to the internet, this graph starts in '89. It's a line that goes at a 45-degree angle up and to the right. Almost every internet graph or anything that you want to graph is going to have this kind of example. So this is BGP routing table growth. This is the number of unique ASNs. This is the number of unique organizations on the internet. There's over 55,000 unique network operators worldwide, which is really not that large of a number. So BGP does have security issues. This talk is not going to really talk about that so much. There was some very good stuff out there including man-in-the-middle attacks from DEF CON 16. There's transitive trust issues. There's really no central authority. There's all sorts of issues around trust and lack of verification on the internet. And this happened, so every so often, because humans are involved, there's issues. There was an issue back in 2004 where this particular Turkish ISP basically broke the internet on Christmas Eve. They basically said, I am the best path to the internet for all of it. And that was great. And there's a write-up on that. There was another incident just this week. You may have heard about this on the news Monday. Any of you were Comcast customers? Yeah. Level 3, somebody made a mistake. It's just human error. It was not a DDoS attack. It wasn't anything like that. They basically mistakenly announced some more specific prefixes, which is to say Comcast was sending them a bunch of smaller announcements, smaller numbers of subnets, let's say /22s or something like that, for traffic engineering purposes. And Level 3 mistakenly sent those out to the whole internet. And what that meant is that basically for Comcast and some others, Level 3 became the preferred method to get to those customer IPs. And Level 3 didn't have enough capacity to take all of Comcast traffic. So that's what the incident looked like from a latency perspective. From the Dyne Oracle folks, they always have very good write-ups on these things. So you know, the incident was handled pretty quickly, within 90 minutes or so. But the internet really is run by the humans. You didn't lose it per se, but you might have not been able to reach certain sites because the pipes were very congested. And like this here shows the latency increase. So from like some of these tests were like 300 milliseconds, and it more than doubled the latency. So you'd have congestion, you'd have packet loss. You wouldn't be able. You might pull up a website and the page just sort of hangs. You get half the page. Maybe the ads aren't loading, so you don't see the rest of the page. That kind of thing. That was the impact because Level 3 just didn't have the capacity to take and route all the traffic for the whole rest of the world coming into Comcast and some of their other customers. Yes? Oh, so the question is about, is there service providers that will rent BGP routers? Absolutely. Like if, I know AT&T will do it. You can do a managed service contract with AT&T, and you can have your own ASN and have your own IP space, and they will happily rent you a router and maintain it for you. They will charge you for that and do that. And that's a viable option for some organizations. There are certainly institutions like hospitals that I've worked with, and mid-sized education institutions. They can't really attract and retain network engineer talent to be able to run all this in-house. It's absolutely something you can outsource, just like any other thing related in IT. So peering. You may have heard of peering. What is peering? So peering is when two different autonomous systems agree to connect somewhere, some mutually agreeable place, with some mutually agreeable technology for the purpose of exchanging routes, usually for exchanging traffic. Because, so here's the big secret. The Netflixes of the world and the Microsofts of the world and the Facebooks of the world, they don't pay Comcast to deliver traffic for them. They're not paying Level 3. They're not purchasing services. They connect to each other, and this is done as peering. So they agree to connect their networks and exchange traffic for business purposes, because Comcast will say, well, We actually do want our customers to be able to reach Microsoft Office 365. So we're going to connect to Microsoft, and they're going to have multiple connections in multiple places at multiple speeds. They're going to connect in as many places as they can at 100 gig and multiple 10 gig. So really, peering is just network operators that can reach each other and each other's peers directly over this connection, but not the internet in general. So again, peering, it's those two network operators, whether they're a hospital and a local college that might agree to interconnect, local ISP, a national ISP, a large content provider. They're just agreeing to connect privately. And they can do that either over private facilities that they are paying for separately, or they can do it over public exchange points where they can do that on a more cost-effective basis. We'll get to that, more information. So you've probably also heard about internet service provider tiers. This is mostly marketing. I'm sure you've seen marketing if you've ever shopped for internet services where, we have the best network. We're a tier 1 network. What does that mean? There's roughly tiers 1 through 3. So a tier 1 network operator, there's a dozen or so worldwide. It might surprise you to know that the tier 1 network operators, they don't pay anybody to connect to the internet. Now, that doesn't mean they don't have costs. They have all sorts of costs. They have people, they have facilities, they have fiber optic cables, but they don't write a check to anybody else that says IP transit on it. These operators are essentially the internet. And this is for historical reasons. Some of them are historical telecom companies, particularly in other countries. Some of them were for their size, and AT&T certainly, CenturyLink, which includes Quest and Savvis, and now includes Level 3, Cogent, GTT, formerly Tenet, Nlayer, Hibernia, so forth and so on. And you can see, as you know, if you follow telecom at all, everybody's always buying everybody else, and the companies just get bigger and bigger. But these companies are the ones that are considered to be tier 1s, and it really is referred to as a cabal. They make it very difficult for anybody else to become a tier 1 because they like receiving money, they don't like to spend money. So they place a lot of requirements on other companies that want to break into this tier 1 market. So they say things like, well, you must be operating on at least 5 continents, you must peer with us in 7 locations, you must meet a minimum traffic volume of X gigabits per second or X tens of gigabits per second. And the important thing that I want you to come away with from this presentation is that connecting to a tier 1 provider like an AT&T or a Level 3 does not necessarily guarantee that you're actually getting a good internet connection. You're getting an internet connection, but oftentimes some of the tier 2s, a lot of the tier 2s, actually provide a superior internet connection, objectively based on measurements. So the tier 2 ISPs and some of the tier 2s are actually much, much larger than the tier 1s. Hurricane Electric is one, PCCW is another. They're huge. They're all over the world, but they haven't broken into the tier 1 club because the tier 1s don't want them to, because they still like to get their money. So they operate very large networks, and they have multiple peering connections. They tend to join internet exchanges, and they actively seek out direct connections with other players. So that means that, like, if you're like a Hurricane Electric customer, you actually have really good connectivity because they, on purpose, because they don't like to write checks to the tier 1s, they route around them, literally route around them by getting their own direct connections with Microsoft and other entities and all the other network operators so that they don't have to write those checks. You look at their POP list, they have like 130 POPs worldwide. You can buy a connection at one of their POPs. Most of those POPs are data centers. They don't do circuits. You have to come to them. You have to contract with somebody else. You either have to buy your own dark fiber or arrange for some sort of Ethernet transport facility, but their bandwidth is very inexpensive, so it's usually worthwhile. The tier threes are like the minimum viable product. Those are the organizations, and some of these are like very rural phone companies and things like that out in, say, Montana, where they have just enough connectivity to work. Minimum viable product to me means that you have at least 2 connections, so that hopefully if one connection goes down, you're still online. I've certainly seen even carriers that only have a single internet provider upstream. So, you know, there are days in which you're like, oh, we just don't have the internet today. Sorry. So yeah, in the past, if you're a tier 3, you'd order circuits from tier 1s. Hopefully the circuits were actually coming across separate cables or separate failure points. I have seen and experienced failure modes from literally all the internet connectivity into a particular state, crossing the same bridge, going through the same conduit on the same cable. Didn't matter which vendor you bought it from. When the backhoe came for you, you were in trouble. So if you want to connect to the internet, you know, you have to negotiate a contract. You buy a circuit from an ISP, get some IPv4 space, hopefully some IPv6 space. You have a firewall. That's the basic way. Again, I recommend that you do BGP routing and get your own IP space. If you're any size business or institution, it'll be worth your while. Again, you avoid your vendor lock-in. You can add and remove IP transit providers easily with short-term contracts. You can join an internet exchange. So this is a big reason why you want to run your own AS and do BGP routing. This is a graph of internet transit costs from 1998 to 2015 from drpeering.net. This is amazing. The cost per megabit of internet access has just dropped and dropped and dropped. You know, double-digit every year. And even today, so this information here shows 63 cents per megabit wholesale cost in 2015. Well, right now, today, there are multiple operators that you can buy internet transit for under 25 cents a megabit. You can literally, and this is totally public pricing, Hurricane Electric. You want a gig of internet access at Hurricane Electric, $500 a month. You want 10 gigs of internet access, $2,000 a month. This is not special pricing. This is like you can talk to any of their salespeople, and as long as you come to them, that's not delivered to your house, mind you, that's in a data center. But if you are a hosting company, if you're a content provider, if you're a business, an enterprise, and if you have equipment in one of these data centers that they're in, or some of these other providers like Cogent, it's well worth checking out and buying that on a wholesale basis. So in the old days, the architecture of the internet looked like this. You had your settlement-free tier 1 national operators, Sprint, MCI, UNet. That there shows you how old this is, the 90s. And you down at the bottom, you connected to a local internet provider, which is usually a local phone company or a local cable operator. There was some regional connections. And it was old technology. It was mostly telco technology, frame relay, ATM, SONET. You're talking about bundled T1s, DS3s, OC3, OC48, even OC2 level. And then Ethernet became prevalent, and Ethernet is the technology that's really driven the cost down. Ethernet is so much less expensive per bit than any of the old telco technologies. The internet today doesn't really have a single backbone. People talk about internet backbones, and really the backbone doesn't exist. It's a series of meshes of different networks. It's highly distributed. There are certainly specific geographic locations in different parts of the world, particularly certain data centers. Like we all know that if Amazon, AWS US East 1 is having a bad day, everybody's having a bad day. But that's mostly because of the companies that have chosen to put their machines and their virtual servers in that environment. But the internet is highly, highly distributed. Primarily, the internet today runs on 10 gig internet links and 100 gig. 200 gig is here now, 400 gigs coming. We're going to have terabit within a couple of years. 10 gig is very inexpensive compared to what it used to be. You can get 10 gig transport links for $3 to $5 grand a month. Anywhere within a state, you can buy 10 gigs of internet, as I mentioned earlier, for $2 grand a month. So much less expensive. Yes? Yep. Yes. Well, May East itself doesn't exist anymore. I believe that was the Metropolitan Area Ethernet Exchange. Yeah, it was in a parking garage. Yeah, that facility was very important to the internet globally back in the 90s. There were literally companies from all over the world that were putting equipment into this parking garage, into a room, so they could all exchange traffic. Today, that area, the Ashburn area, is huge. There's data centers everywhere. There's fiber everywhere. Ashburn is a major internet connecting point, but so is New York City. So is Frankfurt, Germany. There's all kinds of places where there's major pockets of connectivity. Even if Ashburn was wiped off the map, the internet would still work. There'd be some things that would be offline. There'd be some things that would be slow because of capacity. But mostly the stuff that would be offline would just be the companies that only had assets located at Ashburn and no place else. So today, the other big thing that has driven the cost of the internet down is dense wave division multiplexing. Basically just an optical technology that allows you to run multiple colors of light over the same fiber optic cable. And there's all sorts of commercial systems that'll run 96 separate wavelengths, and each wavelength can be 100 gig. Actually, today each wavelength can be 200 gig. So you can get enormous capacities over just 2 fibers in a cable. And there's all sorts of cables out there that, in something a cable the size of your thumb, you can have 288 pairs of fiber. There's all sorts of technologies that have enabled the internet growth. Modern internet architecture looks more like this. There's these IXPs, internet exchanges, there in the middle. You have the other big thing that's happened with the internet over the last 10 years in particular is the growth of all of these content distribution networks and these huge content providers. Who here is using Netflix at home? Like I expect almost everybody's, okay. Or using some other form of video streaming service. Netflix by itself, for the average residential network operator, Netflix is 30 to 40% of their traffic at night. Just that one company. At night, well, or whenever peak utilization is. Other companies like Apple, when there's a new iOS update and a new iPhone drops, all the internet exchanges in the world all set new peak utilization records because of all the people. Mostly it's your phone doing it automatically in the background. You don't even get a choice. They're just downloading all that traffic. And so you have these huge content companies, and you have content distribution networks, companies like Fastly and others that they are in the business of providing content hosting to companies like your newspaper, to companies like CNN, and anybody else that has a very high traffic website. The companies that have high traffic websites, most companies cannot handle hosting all that traffic themselves, or particularly if you have a big event, you have a major news crisis, or you've got something like the Olympics, you have to work with other partners. So those content hosting companies, they use internet exchanges mostly to distribute their traffic. So what's an internet exchange? Well, there's basically an internet exchange is just a facility. It's usually pretty boring. It's really just like any data center you've ever seen. It's a rack with some equipment and some switches. It doesn't look very sexy, but it's very, very important. It's a place that enables 2 or more autonomous system operators to interconnect. A lot of the content distribution networks, like to place physical hardware in the IXs. So for example, Netflix, they have thousands of their OpenConnect appliances distributed around the world, a lot of them in internet exchanges, so that when you're connecting and you're watching your TV show, you're actually getting those bits from your show delivered through a local exchange. They're not coming from California or New York. Yes? Ah, they are running FreeBSD. Yes, because of many superior reasons. Actually, there's a really great blog post on how they're able to achieve 100 gig throughput on a single server. So the internet exchanges, there's HearingDB has 542 internet exchanges worldwide. They're all over the place. They're often in data centers, telecom, hotels. There isn't one in Delaware that I could find. There's certainly one in Pennsylvania. So these internet exchanges today are really the primary way that traffic gets moved around the internet. And many of these exchanges are operating at huge levels of traffic, more than a terabit a second worth of traffic. Some of them are carrying over 5 terabits a second at peak. Peering gets political on the internet. There's definitely companies that will not peer with each other, and I mentioned how the tier 1 folks don't really want to make any more tier 1s. And there's companies like Cogent and Hurricane Electric. They don't peer with each other on the IPv6 internet, and this is something like most people don't know, that if you actually want a full IPv6 internet connection, you have to buy a connection from both Cogent or Hurricane or somebody that peers with both of them, because you can actually get in a position where you can only connect to about half of the v6 internet because they have a long-running battle. Here's some infrastructure maps, or things you can look at later if you want to look at the presentation about where all the fiber optics are and the submarine cables around the world. There's all sorts of them, and they're being built all the time. The big thing today, in the past, all these submarine cables, almost all of them were built by telecoms. They were built by phone companies. This is all changing. It's the content providers. It's literally Facebook and Google and Microsoft and others. They are building these cables now, and then they're renting capacity to the phone company. Because, seriously, because Facebook and Microsoft and Google certainly, and Netflix, well, Netflix doesn't build their own, side discussion, but they have far more traffic than any of the phone companies ever had and ever will. So it's in, and basically smart folks, both in network engineering and in accounting, figured out, wait a minute, we're this phone company's biggest customer. Why should we be buying things from them? Why don't we make them buy from us? They contract for it, yeah. They hire companies like Siemens and others to construct these systems for them. There's a major one being built on the East Coast now, from, I think it's North Carolina or South Carolina over to France. There's another major cable that's getting built going to Japan from the West Coast. And these are being owned by consortiums of Facebook and Microsoft and Google and others. This is some traffic graphs from DKIX Frankfurt, the German Internet Exchange. They have about 700 members. You can see the growth over the last 5 years. They're routinely over 5 terabits a second of traffic. One of the other major internet exchanges in the world is in Amsterdam. In the Netherlands, they have 800 plus members, AMSIX. Again, they're routinely peaking over 5 terabits. In New York, the German folks opened a New York exchange 3 years ago. And you can see there how it's grown from nothing to over 200 gigs a second worth of traffic. Yes? Yep. Yes. No, it's pure politics and money. It's not technical. Yeah. Nope. There may be, well, that's depreciation of assets over time is an accounting issue, which becomes a money issue, which becomes a political issue. I have certainly personally seen phone companies make stupid decisions because they say, well, this asset has 3 more years of depreciation left on the books. So we're not going to do the right thing. But Magpie is in Philadelphia. They're actually the local Internet 2 gigapop. There's a whole bunch of local institutions that connect to that. It's run by Penn. Running out of time, but I'm going to blow through the last bunch of slides here. This is a graph of connectivity of a sample small internet provider. This happens to be AS33278, or say 33728. Actually, one of my clients. They have 3 upstreams, and this just shows how generally the internet can function and be connected. I can read all these. You guys can't. 7018. Well, that's AT&T. Cogent here. That's Hurricane Electric. That's old UUNet. I used to know a lot more of them, but this is what Amazon's connectivity graph looks like. Slightly different. They actually have 269 direct peers, meaning that Amazon has 269 different operators that they are choosing to connect with directly. It doesn't cover how they get the rest of the internet. But for their own reasons, they found that there's 269 networks that's worth it to them to connect to. They can be tier 2. They could be end users, end user institutions. And you could go through the list, and this is all available on different public websites. This is all information that is easily discernible from looking at the routing table. There's all sorts of websites out there that basically look at all this data and analyze it and present it and visualize it for you. Let's talk about how the internet keeps working. So Anycast, so how many people here have ever used Google DNS? 8.8.8.8? Okay. So why do you do that? Because it works, right? Well, why does it work? Is it because Google's really awesome and they have like this one server? Yeah. So, well, it's even beyond that. Now, you've probably heard of server load balance clusters, where you have like a website or some sort of service, and it's running on multiple servers at the same time for load balancing purposes. That's great. That's awesome. But that's limited to one physical location. What Anycast allows you to do, and Google uses this and lots of folks use this, is you are sending out the same IP subnet and injecting it in multiple places on the internet. So the 8.8.8 server that you might connect to in Delaware is an entirely different server than you're going to connect to in Denver. It's a different server than you're going to connect to in France, because they have multiple instances of that server running in different locations around the world, and Anycast allows you, your network operator or your ISP, to connect to the closest one. Same thing for the root servers. I don't know, anybody here know how DNS works? Does anything with DNS? Okay, a couple of you. I'm not going to go through a whole lesson of DNS. We don't have time, but there are 13 root DNS servers in the world. They're letters A through M. These are the servers that actually provide the master directory information for when you go look up a website like CNN.com or any sort of .net or any website in the world. It has to come originally from the root servers. So this is not a matter of there being 13 individual servers. They're clusters of servers with load balancers and many Anycast instances. Some of the root servers actually have 160 separate physical instances around the world, and each one of those instances could be a cluster of servers. So it's highly distributed, highly load balancing, and this is what's allowed, in part, the internet to scale. The root servers, each one of them individually is handling billions of queries a day. It's ludicrous, the traffic level that these servers handle collectively. And without these servers operating, basically the internet doesn't work from a functional point of view. It will still pass traffic based on IPs, but Humans don't remember IPs. We remember names. So these Anycast root instances are often located at internet exchanges around the world. Why do you do that? Well, improves geographic diversity, improves performance by getting to the closest servers, so lower latency. This is also how DDoSes are often helped to be mitigated, is when somebody, particularly if it's somebody with lower power attacks, it's not like a Krebs level attack. If they're sending a few tens of gigabytes worth of DDoS traffic to a particular DNS server, if it's anycasted like the root servers are, it's going to be distributed around the world. It's not going to go to any one particular server. It also allows you to improve availability and resiliency. You can take a cluster down and just the traffic gets rerouted automatically to the next closest server. A lot of network operators and content companies do this at the data center level. Not only can Facebook shut down a whole cluster of servers, they can just take an entire data center offline. They can just be like, we don't want to use that data center anymore for the next 3 hours because they need to do some maintenance or something like that. They have that ability, and Anycast is one of the techniques. Very quickly, here's some statistics about the internet. Over time, back in '92, this is from Cisco, is estimated that the entire internet was 100 gigs a day worth of traffic. In 2015, it was 20 terabits per second worth of traffic worldwide. 58,000 ASNs, all sorts of other statistics you can look at. The big driver of content on the internet is certainly bits, is certainly video. Cisco is estimating that there's going to be, basically 82% of all traffic will be video one way or another by 2020. Speeds. So very briefly, Akamai State of the Internet report, I highly recommend it if you're interested at all in internet metrics and performance. They do a really great job. They issue it multiple times a year. This graph here is connection speeds. That lovely high graph at the top, that is South Korea. South Korea has the best internet access in the world because it's almost all fiber optic. It's routinely people have gigabit or even 10 gigabit connections at their homes and offices, and it's cheap, like sub $100 US per month. The blue line at the bottom is China. The US and United Kingdom are there pretty close together, yellow and red. Peak global connection speeds, again, South Korea is the best. Here is some more local stuff in the US, and you'd be surprised that actually Delaware does very well nationally in terms of connection speeds average. Better than the United States on average. The United States is in the blue. Where I come from, Maine, is in the red. Maine actually consistently ranks 49th or 50th in the country for internet speeds. I am doing everything I can to fix that, but I have to get the companies to agree with me. So that's a good question, and that's an important point. This data is real data. This is not a survey. This is not an estimate. This comes from Akamai. Who here knows what Akamai is as a company? Okay, so they are one of the very first content distribution and internet content acceleration companies. They have servers everywhere, all over the world. A lot of your retail websites that are out there, your shopping websites, you're going to go buy a sweater or something. You go to lolbean.com, all those beautiful images of the boots and things, those are coming from an Akamai server. I know this. I know that they're an Akamai customer. It's public knowledge. Akamai generates the data for this report. They metric and monitor every single connection to every one of their servers. They record it. And they are able to do statistical analysis. So when they say this is what the speeds are for these states, they're doing that because they have all the data from the connections, and they're able to geolocate the customers. You can get different services that you can subscribe to that will tell you with different degrees of accuracy where that IP address is coming from. So they can fairly accurately say, yes, Delaware has very high-speed connections based on measurements off of their servers. Now, they're not the whole internet, but they have so many websites, hundreds of thousands of websites that they're accelerating, that this is a pretty good proxy. It's basically about as good of data as anybody has for how fast the internet. So I'm out of time, but I'm going to say, so why is the internet still working? How is this thing that started off as a DoD research project in 1969 and was converted to TCPIP in 1983, how is it possible that we have this decades-old network running decades-old technology still function? Well, Moore's Law has a lot to do with it. Because of Moore's Law, we have faster computers and more RAM. So the routers were able to get faster, to process the packets faster, to deal with the growth of the routing table. We had some technology that allowed us to do incremental upgrades, so we didn't have to rip and replace. So in the telco world, in terms of Sonnet, we were able to scale from OC3, 155 meg, all the way up to OC 768 at nearly 10 gig, and we could do that in incremental stages. Same thing with Ethernet. It's fundamentally, Ethernet hasn't really changed, even from 10 meg, 100 meg, gig, 10 gig, 100 gig, and now we have 200 gig coming, and terabit will happen. It's still fundamentally the same technology, and it's become commoditized, so we're able to do incremental upgrades. So that's a big reason why the internet still works. It's because of investments in fiber optic cables by different carriers, the submarine cables in particular, but also the fact that they put so much fiber in the ground, and we've had new technologies that have come along in the last 20 years, such as dense wave division multiplexing, that allow us to get more bandwidth out of the same cable. Back in the old days, when you ran a 48 count cable, each pair of fiber you could run one service on. So you could run like a single OC3 on 2 fibers. Well, today, with technologies, we can take exactly the same cable that's been in the ground for 20 or 25 years. We can put new electronics on both ends, and now we can run 96 wavelengths of 200 gig on the same exact fiber that used to run 155 meg. So that's amazing. That's huge that we've been able to do that. The other reason the internet keeps working is because of decentralization of services and content. Anycast that we talked about, scalable root DNS infrastructure, the internet exchanges that have come into play that didn't exist. I mean, internet exchanges did not exist at all 25 years ago, and they've certainly accelerated in the last 10 years. That's enabled more and more local content and more local access and more data center facilities for these content distribution networks to build out their servers at scale. So because of all of these things put together and that geographic load distribution, the internet continues to work at scale. But really, the primary reason the internet continues to work is the humans. Even though we break the internet sometimes, and I'm one of the network operators that I can say I've broken the internet from a local point of view a few times, but it's the Internet Engineering Task Force, NANOG, and other network operator groups, which are primarily volunteers, passionate volunteers. It's a lot like the open source world. It's because we continue to share best practices, have conferences, talk to each other, and there are folks that are continuously inventing and deploying new solutions. Things like NAT and PAT and NAT6.4 for V6 to IPv4. These sort of things, these are all inventions that engineers faced with problems, a lot of them at network operators at these large global scale companies said, well, how are we going to do that? And then you get a bunch of guys together and gals and you have a few beers and things get written on cocktail napkins and pretty soon you have another RFC. So that's my answer. And I have a whole bunch of bibliography and this slide deck will be available. I'll put it out on Twitter, and thank you very much. And if you have any questions, I'd be happy to take more questions. Yes? There is. They've done some very interesting things in labs. I mean, companies like Corning, they make a lot of glass product. They actually do a lot of R&D on fiber. There's definitely some sort of physical limit, but each individual wavelength of light, in labs, they've been able to do terabit level custom stuff, and that's on a single wavelength. And when you can run multiple colors of light over the same fiber, I can foresee a point where, we're definitely, with today's existing technology, you can get almost 10 terabits over 2 strands of glass. Maybe that will scale up to 100 terabits. That's a lot of data, a real lot of data. And that's just on 2 strands. And most of the network operators that are building, if you build today, you're putting up a high count cable. And what I mean by a high count cable is it's maybe 288 at minimum. There's cables, they have this thing called ribbon fiber that's maybe this big around. It's 3,000 fibers packed inside that cable. And that's the stuff like they're running in New York City. Most of the cost, as you might expect, of running cable, what's the cost? Labor. It's the people and the trucks and the crews actually digging and installing stuff and conduit, whatever they're doing. It's all labor. The cost of the materials is almost insignificant. So if it's 2x the cost to go from 288 to 488, or go to 3,000 count ribbon, if you're thinking long term, you're going to put in the highest count cable you possibly can, even if you don't need it today, because that cable is going to be good for 30 years, maybe even longer. Typically, that's good. Typically, like 24 to 96. That's your typical neighborhood feeder cable. It depends. So, if it's drop wire, like to your house, and some of you folks probably have fiber to the home. There's people doing it. The fiber to the home cable is going to be like either a 4 to a 12 strand. You only need one. Yes, you had a question. Ooh, it's a good question. They have the great firewall. It's very centrally controlled through the government. They know where all of their exits are, and they monitor them, and they're doing protocol inspection. And I don't know. That it's something you could research. No, there's multiple. Yeah, they have it controlled. They connect through Russia. They also provide, like China provides one of the connections for North Korea. Russia provides the other one, which is brand new, incidentally. Yes. Yep. Mm-hmm. Yeah, so I can give you kind of a high-level architectural review. So your cable modem networks, all your cable operators, they operate on what's called a geographic node basis. They built their networks as fiber to the node, meaning basically fiber to the neighborhood. It's still traditionally copper coax. So that node may cover a subdivision or it may cover a section of town. And that typically is going to be anywhere between 100 customers to maybe 500 to 1,000 customers on that one node for that cable modem system. So you're sharing bandwidth at some level. And it may be with a few hundred customers, or it may be with 1,000 customers. With fiber to the home products like Fios, you have your own dedicated fiber connection where you're sharing your fiber, the passive optical network, but you're sharing it with much less people. A PON network is going to be typically 32, 64, or 128 customers on that optical network. And the PONs are either 1 gig EPON, 2.4 gig GPON, or 10 gig EPON technology. So fundamentally, just from a division of the numbers point of view, on a fiber network, you're sharing that bandwidth with far fewer people in the local access layer. That doesn't cover the bandwidth to the internet provider. If the internet provider themselves, your cable company or your phone company, if they don't have enough bandwidth to the internet, it's going to suck no matter how good the math is on the local level. But that's the big problem with cable today is, and you can feel it in a lot of places when like kids come home from school, you know, 3 o'clock, 4 o'clock, or when people are, it's peak Netflix viewing hours. Some of that times when you're getting buffering or the picture quality degrades, that's not because they don't have enough bandwidth to Netflix. It's because the bandwidth in your neighborhood is saturated. And they need to, and the way they do that is they divide the nodes. And cable companies do this all the time. I've seen it. I've worked with some of them. So they'll take a node that has 1,000 customers and they'll put in a second node and they'll cut it in half. So now there's 2 nodes of 500 customers each. And that's great. And that'll work for another couple of years. And then they have to do it again and again and again. And it's all a matter of just, you know, having fewer and fewer people sharing the same bandwidth. So, right. Thank you so much.